Hmm. Good morning. I would like first to thank Professor Mastorakis for inviting me here, and I'm happy to have such a distinct audience. Uh, my topic is mainly um, fundamental mathematics, but there is also a lot of computer experimentation in it, and it concerns. It's the topic is conformal self mappings of fundamental domains of analytic function. Um, then there are a few words here which need to be explained. Then conformal, we are in the field of complex analysis. Then we have functions from the one complex plane to the other complex plane, and the mappings are such that the angles of curves are preserved. This is conformal. Um, what is a fundamental domain? That's a more complicated thing. Fundamental domains were related to the theory of automorphic functions, meaning functions which are invariant by a certain group of transformations. And then a fundamental domain is a domain which is mapped by the elements of the group on one of each other. But Alfors gave to this concept a new meaning, namely allowing any analytic functions to have fundamental domains. And he said he understood by fundamental domain a domain which is mapped, conformal mapped by the function on the whole complex plane with a slit. Now, what is a slit? Imagine that you have a sheet of paper and then you pick up a scissor and you cut it. What you obtain is a slit. In complex analysis terms, it means that you cannot cross the cut, the slit. You cannot cross by the values of some function. And this is the idea that any analytic function uh, divides the complex plane into fundamental domains. And there are number n of domains if the function is a rational function of degree n. Otherwise, if it is another non-rational functions, the number of domain is infinite. I will try to show you a few examples of such such domains. I use here in this paper also theorems of classical complex analysis, which I suppose that are well known. Now here, in these pictures, I took Blaschke product of degree 9. What is a Blaschke product? It's a product of Blaschke factors, and the Blaschke factor is a function, the simplest function, complex function, which is of the form z minus a over 1 minus a bar z. Then a Möbius transformation, and we have a certain number of these Blaschke factors. If the number is finite, then we call the product finite Blaschke products. If not, then we have infinite Blaschke products. Now, for the infinite Blaschke products, certainly we have to put a condition of convergence. And Blaschke found a very simple condition, namely, if the elements are akz, ak minus z over 1 minus ak bar z, then the summation of ak should be convergent. Obviously, we only talk about convergent Blaschke products. And in this case, I have taken Blaschke products of degree 9. And I try to portray the fundamental domains. The construction is based on two theorems, let's say, about Blaschke products. First theorem says that the equation, if the Blaschke product is B of Z, the equation B of Z equals 1 has all the solutions on the unit circle. Then you have here these solutions. I denoted them by zeta, zeta1, zeta2, and so forth. There are 9 of them. And remember that the value of the function in each one of them is 1. Now, if we start from 1 and go vice versa to this picture and move the point from 1 towards 0, then the corresponding points on this plane will move toward the origin, as is shown in this picture. If we continue, then these curves will meet in some branching point. That's self-understood. This is a branch point, this is another branch point, so on and so forth. And since the product contain also z cube, then some of them will meet in the origin. At this stage, not all the branch points have been connected, and then we have to do some more continuation, and we arrive here to connect all the branch points, except that those who have been also connected will have some more continuation, which do not harm the image in general of what happens here. Now, at this point, all the branch points are connected, and they divide the unit circle, the unit disk, into 9 domains. Look, if we take one of them and we go on the unit circle from one point to the next one, okay, since the value of the product is 1 in each one of these points, then this arc will be mapped 1-to-1 on the unit circle. If so, then the domain here, based on another classic complex analysis theorem, the domain here will be mapped conformally onto the unit disk. And this happens for each one of the domain inside the unit circle. Now, if we do a symmetry of these domains with respect to the unit circle, okay, we obtain we obtain new domains. For example, the symmetric of this domain is this one, okay, of this one is this one, and so forth. And these domains cover now the whole complex plane. There are 9 of them. Some of them are unbounded, like this one. Some are bounded, and so on. Now, each one of these domains is mapped by the function onto the whole complex plane with a slit alongside the real axis. This is one simple example of what fundamental domain can be. For this a simple function, which is a Blaschke product. There are some other classic functions, like, for example, the exponential function. The exponential function, f of z equals the exponential of z. Okay? Now, if we look at the values of this function, we notice that they are the same in each one of these strips. They are the same, and they map the strip, each one of the strips, onto the whole complex plane with a slit alongside the positive real half-axis. Here we have the function cosine. The fundamental domains are these vertical strips. They are mapped also, conformal mapped, on the whole complex plane with a slit alongside the real axis, complementary to the interval -1, 1. Okay. Now let's go to some more complicated functions. Here we have Euler gamma function in this part, and I took also the Riemann zeta function. I put them next to each one because the picture is somehow similar. But there are a lot of other complications when we go from gamma function to the zeta function. Here, the fundamental domains are these strips bounded by these lines of the same color. If we take black color, then this is a fundamental domain. It contains a red one, which is the preimage of the negative real axis. But we can take also the domain between two red lines. And this is just an affirmation that the fundamental domains are not uniquely determined by the function, but what happens is that some points of these domains are fixed. We cannot see that on the gamma function, but we can see on some other functions, and these fixed points are the branch points. The branch points are, in fact, the zeros of the derivative of the function or the multiple poles. I go further to some other examples, and this here is the well-known modular function. The modular function is, in fact, built by taking fundamental domains. And these two domains, omega and omega prime, are mapped by conforming to Riemann mapping theorem. There is a unique function which maps these domains onto the upper half plane such that some points, 0, 1, infinity, are permuted. And if we do reflections with respect to each one of these lines, here the vertical lines, but also with the circles, then we obtain some other fundamental domains for this function. Notice that these domains accumulate to every point of the real axis, meaning that every point of the real axis is a singular point for the function. Therefore, it cannot be continued across the real axis. Here we have another example, interesting example, which is the Weierstrass pi function. This series represents the function. We can check that it is a doubly periodic function with the periods omega 1, omega 2. And if we try to find the fundamental domains of these functions, they are these half of these parallelograms, and they are mapped. For example, this triangle is mapped on this picture here, and we have three cuts here from E1, E2, E3 to infinity. And the examples can continue indefinitely. But I would like to insist on a special class of analytic functions, which are the Dirichlet functions, one of which is the famous Riemann zeta function, which is well known for the Riemann hypothesis. The expression of a Dirichlet function, a Dirichlet series, is this, given by the formula 3. Here we have two sets of parameters. An represent the coefficients of the series, and lambda n represent the exponents. Lambda n is an increasing sequence of positive numbers. And this series converges at the right of vertical line, passing through the value sigma c on the real axis, and this is the convergence abscissa, and it can be any number between minus infinity and plus infinity. Anyway, if this number is finite, then there is the possibility to extend the function at the left of the this line into a function defined on the whole complex plane. And this will be a Dirichlet function. I gave in some other papers, I gave a sufficient condition for this extension to be possible. Now, subclass of this function is those which are defined by so-called Dirichlet characters. And these are the numeric functions, arithmetic functions, and I took modulo some number, and I took here a character modulo 7. You see the values, the possible values of this. Omega is root of order 3 of the unity. And if for an we take lambda of n here, chi of n, then we obtain a so-called Dirichlet L functions. Now, the Dirichlet L functions are well studied, and there are packages of computer programs giving the values of these functions. And this is why I consider only Dirichlet L functions, because I could find the values of these functions. We denote them by L of chi and s, and therefore we have chi of n here, and n to the power s as the denominator. Obviously, zeta of s is one of them, where chi of n, where n is 1, and therefore we have this expression for the respective function. Now, what is interesting for these functions is that if we take the preimage of the real axis, then we obtain these curves. And here we have the preimage of the real axis by the L function defined modulo 7. The L function modulo 7. And the two functions, one is chi 2 of n, and the other is chi 4 of n. The difference is that one has real coefficients and the other are complex. This is the real one, and this is the complex one. The real one contains the real axis as the preimage, while the complex one does not contain it. This is important fact because starting from these lines, by another interesting construction, we can obtain fundamental domains. Then the fundamental domains will be bounded by the lines here, which are only in blue. For example, this one and this one, okay? And And there is something that we have to construct here in order to obtain the whole boundary of the function. This is a more complicated problem, and I don't enter into details. Another fact is that we can represent the preimage of the complex plane by these functions by using colors here. And in this preimage, we have the zeros of the function. We have also the part which is corresponds to the upper half plane, the lower half plane, the intensity of the color marks the distance from the origin, and so on and so forth. And this gives more detailed representation of such a function. Okay. Now, let's go to my problem, which is representing fundamental domains on themselves. As I noticed from the beginning, this appears to be a straightforward problem, because by Riemann mapping theorem, we can take the representation of the domain on the standard domain, which is the unit disk or the whole complex plane or the Riemann sphere. And then if we take two of these functions and compose one with the inverse of the other, we obtain a self-mapping of the domain. But this is just a theoretical possibility, because the Riemann mapping theorem gives no hint about the form of the functions whose existence is proved in the theorem. And therefore, trying to find some other way to map conformally fundamental domain on themselves is not a trivial problem. And I proposed the following one. We take a Möbius transformation, denoted here by M, and we construct this function, chi M, which is the inverse of the function which exists in the fundamental domain, because the mapping there is bijective, composed with M and composed with F. You realize that this move the points of the fundamental domain into the fundamental domain. And also a nice feature is that we immediately have the form of the inverse function, which is this. Then all we have changed is M by M to the power minus 1. And I have, this is the first theorem. The first theorem, which says that chi M is a conformal mapping of this domain, omega minus a slit here onto omega minus another slit, in such a way that now omega minus a slit means a double connected domain. And therefore, these functions maps double connected domains, one of each other, and in such a way that the boundaries of this domain correspond as shown here. Now, with this in hand, we can try to compose such a representation, and we obtain group properties. There is another fact, interesting fact, mentioned in theorem 3, which, or 2 here, which, no, 3, which deals with the fixed points, of such a mapping. Then the fixed points are not arbitrary, they are related to the fixed points of the Möbius transformation M, with the help of which we constructed chi-m. Okay, and I will go further. First of all, mentioning a classic result about Möbius transformations. Möbius transformations are completely characterized by that picture. We have here this Möbius transformation, okay, 11, and the picture we have here is the characterization of this transformation using a net of circles. These circles are the so-called Apollonius circles here, and these are orthogonal circles passing through the fixed point of the transformation. And now with the help of this, I realized the first self-mapping of the fundamental domain here on itself. And this, you see how the Steiner net represented previously is transported on the fundamental domain, and it shows the way the points are moving by this function one to each other. This way is given by the arrows represented here. And here we have another example. Okay, and here we have something related to the cosine function, the same representation, which is very suggestive of the motion of the points inside the fundamental domain. And now this is the most interesting picture. And I should tell you that my collaborator worked about a week on this picture. We knew from the beginning what we have to get, but the drawing itself was very hard to obtain, and this is why I called also computer experimentation this paper. And this is one of the functions, Dirichlet function I mentioned previously. And in the interval taken here, there are several fundamental domains. We cannot see them. We cannot see them, but because the construction of this domain, as I said, is somehow complicated. But what we see is the motion of points toward the fixed points, or repelling the fixed points. Okay, and this picture gives us an idea of what the fundamental domains are, because it's certain that this fundamental domain should have the boundary passing through this area, one of them, and another one passing to this area, and so forth. And thank you.